Okay, so now that we're hopefully well acquainted with our fall velocity, we can start to explore this thing which I introduced, this Lorentz factor gamma, in a bit more detail. So if you'll recall, we had that the fall velocity we simply defined as the proper time derivative of any world line when we parameterize our world lines using proper time, where we said that proper time is just the time that you measure when you're stationary in your own reference frame. So if this x hat is our own reference frame and we're stationary, just simply our world line travels along a time axis, then we simply measure proper time and our world line points straight up, and hence so does our fall velocity, just simply points straight in the time direction with no space component. So we saw that we could define in general the fall velocity components, where now this v could potentially be a three-dimensional vector, say, if we're working in 1 plus 3 dimensions. And so I'm just kind of representing the other three components of this now fall vector, just using a kind of shorthand to denote the space components by a single spatial vector. Remember, it has a spatial index only, but just for simplicity we don't need to worry too much about higher dimensions, and we can just stick with 1 plus 1 dimensions. So now this is in general any fall velocity. We're going to have a space component where this v is giving our coordinate velocity, or the velocity at which you're measured to be moving through some reference frame. So this would be a general fall velocity. If we now realise that in our own frame, I'm going to denote our own frame just with a hat so we can keep track of what's what. Now in our own frame, this coordinate velocity is obviously 0. We don't move through the spatial coordinate of our own frame at all. The fall velocity has no space component, it just points completely up along the time direction, and so its expression is simply this c gamma. So why don't I now write, in our own frame, this is our kind of stationary fall velocity, or spatially stationary. We still have some velocity through space-time, we're still travelling through time, but we just are not travelling through space at all. So that's in our own frame. But if we were to now say transform, we haven't actually discussed how we do this yet, but we can already just think about it. What if we now look at how this fall velocity appears in some other frame, say a frame that's going to be moving with some velocity relative to this frame? Or another way we can think about this is we choose ourselves to be stationary in now some other frame. Let's say we're the observer A, and we look at this observer B, who's stationary in their own frame. But now from our perspective, our newly stationary perspective with unhatted coordinates, we might see this B observer moving in some way, travelling along some world line. And we kind of started discussing how we can use the proper time to always parameterize this world line. And I've started to introduce you to the idea about how this length, this fall velocity, is then going to be distributed between a time and space component in this new reference frame, because we have the fundamental realization now that the length of this fall velocity vector is always fixed. We say that the fall velocity is normalized because we can first of all define its length by simply using the metric, and we know that lengths measured by the metric have to be invariant. And so the length of your fall velocity vector is essentially always fixed by its length in your stationary reference frame. And so we can now start using this fact to look at how that length is going to appear in some other reference frame. So I said we're going to transform without really knowing how we do that yet. We're just going to think roughly, but we're going to transform now this 4 velocity into some other frame. So if you like, we're taking this stationary 4 velocity vector and we're translating it now into this other frame, and we're going to look how it appears in this new frame. So in the new frame, we're going to have, again, the first component C gamma, and then whatever this now potentially non-zero velocity is going to be, if this 4 velocity has some spatial components. So without knowing how we do this transformation, we're going to see that coming up, but we can already know quite a lot just from simply looking at the fixed length of this 4 velocity. So we said 4 velocity is normalized. If you'll now remember, we defined the length, just using this kind of shorthand modulus notation to denote the length of the 4 velocity. We compute this by essentially plugging in the 4 velocity 2 copies into the metric. Hopefully this expression is familiar, and then we simply perform that operation. We can think about it fairly easily. And so the length of our 4 velocity in our own frame, of course we have no space component. I would have in general written down the length of now any 4 velocity. So the length of our 4 velocity vector is given by this expression, and we know that lengths have to be equivalent regardless of the frame that they're measured in. And so in our rest frame, our stationary 4 velocity is simply just going to have the length minus c squared gamma squared. Okay, and now if we just remember how we defined this gamma initially, well, when we took these derivatives to work out what the 4 velocity is, we saw that this gamma component is essentially the derivative of the t coordinate with respect to the tau 4 velocity. And then we saw, using the chain rule, how we could sneak in another factor of the gamma down here in the coordinate velocity component. So this gamma dt by d tau, I'll just write that up here so we can see it a bit clearer. We simply identified it using the chain rule, and this is just how we defined it. But now let's use these expressions to maybe arrive at a slightly more useful expression for this gamma. So we said in our rest frame, we can already know what this gamma is going to be. Essentially, in our rest frame, this coordinate t is tau, so d tau by d tau is just going to be 1. And so we now realise that always this 4 velocity length has to be equal to minus c squared, regardless of whether you're measuring it in your own frame or any other frame. Its length is always fixed to be minus c squared. And so now, just using that, comparing with this expression, if I just make a bit more space. So we know that our length of the 4 velocity is always going to be equal to minus c squared. So let me just rewrite what I had previously. I had that the length of now any 4 velocity, not necessarily the rest frame 4 velocity, but the length in any frame, is going to be just plugging in the expression we had before. Again, using the metric. If you're not familiar with this, go back and check in some previous videos. But now we know this length has to be equal to minus c squared. And now we can just do some algebra, rearrange this expression. So if I collect the gamma squareds on one side, And if I now divide by, well, I'm first going to multiply by -1 to change these around, and then I'm just going to divide by this bracketed expression to arrive at this. And now I can simply divide everything on the right hand side by c squared. And I'll arrive at the following. So I've arrived at the following expression, that gamma squared is this 1 over 1 minus v squared over c squared. And now to give it its more traditional appearance, we usually see it with the square root, like this. And this is now how you usually see the Lorentz factor presented. We now express it simply in terms of this coordinate velocity. So this is now an incredibly useful and powerful expression. We're going to be seeing this cropping up a lot now. We're going to see where, well, we've seen now where this expression comes from. We can realise it from the normalisation for velocity, which is a fairly fundamental fact. But we're going to see how we can have some nice ways to interpret this expression. So before we move on, I just want to make a few comments about this now. So I'll just rewrite what we just derived. This Lorentz factor. So this Lorentz factor, which we're going to see a lot of, so it's useful to start exploring it and getting a feel for what this function is doing. So the only real free parameter we have here is this v squared, the coordinate velocity of some frame. And now let's just quickly have a quick plot of this function. We can see it depends on the v squared, so it's not really going to matter about the sign of v. So I'll just consider positive v's. But basically, at v equals 0, this thing is just 1. And then as v increases, this is going to start increasing upwards. And now as v approaches this value c, this thing, well, the denominator is going to approach 0, and so this thing is going to asymptote to infinity. And so this function now, this gamma of our velocity, if this is our velocity, is going to look something like this. And it's going to have a vertical asymptote at a value of v equals c. So as v approaches c, this gamma becomes infinite, and as this v becomes smaller, much smaller than c, and this gamma just simply stays at around 1. So it's not until we approach v equals c that we start significantly deviating from this gamma equals 1. We're going to be able to see that this gamma is effectively, or a way that you can interpret this gamma is it's kind of controlling how much or how relativistic your system is becoming, and the relativisticness or the relativistic factor of your system drastically increases the closer your velocity gets to this velocity c. But for low velocities, this v squared over c squared is basically negligible, and this gamma is essentially just 1. But now, what is this gamma really doing? Well, to see this in more detail, we're going to need to start discussing Lorentz transformations, so I'm going to put off that discussion till then. But we can already start getting a feel for this if we remember how we defined gamma in the first place. We said that this gamma was this derivative of our time coordinate with respect to the proper time. And so now you can kind of intuitively think about this now as being how much is the coordinate time varying, or how much is it changing as this proper time is also changing. So if gamma is just close to 1, i.e. we're somewhere down here with a lower velocity where v is much less than c, if that's the case, then this gamma is simply 1, the time coordinate is not going to be drastically different from our proper time, but as this gamma starts increasing, we're going to see that now if we just kind of consider the fixed version of this formula, or just consider integrating this formula, we can see that as this ratio starts becoming much, much greater than 1, for a fixed interval of proper time tau, we're going to see that the coordinate time interval is going to be much, much larger than the proper time interval. And the fact that gamma kind of limits to 1, it never goes below 1, is another way of interpreting the statement that proper time is the minimum possible time, because you can just now restate this as the coordinate time interval is now proportional to this gamma times the proper time interval. So if gamma, its minimum value is 1, proper time is always less than or equal to this coordinate time interval. And so now quite a nice way that you can kind of reinterpret this expression. So now another quite nice way that we can interpret this expression is as the following differential equation. So we can say that the increment d tau is going to be given by essentially dt over gamma, or the following expression. And now one thing we should always keep in the back of our minds is that this v is a function of t. It depends on the coordinate time parameter, because remember v is dx by dt. And so how you should really interpret this expression now is the following differential equation. So then this is now another way to interpret the proper time. Essentially the proper time is just now the solution to this integral. Really, I should say that this is now a proper time interval between some two coordinate time intervals. And so however we would solve this integral, probably numerically, but we can now see that the proper time is just going to be coordinate time if this v squared over c squared is so small that it doesn't enter into this root at all, and then we would just find that delta tau is delta t. But now as v approaches c, this is going to have a non-trivial solution, and we can see that it's going to correspond to essentially a ratio gamma between these two differentials. So this is just another way that you can view or define proper time. It's not really that nice. I think the other definition is much nicer, but now just showing it to you. But really what we should take away from this now is the definition of this gamma. You can see it quite clearly depends on the coordinate velocity. And so when we start exploring now transformations between frames that are moving with different velocities, we're going to see how this gamma is going to come into play quite heavily. So then in summary, we've revisited this Lorentz factor that we introduced in the definition of full velocity, where we simply introduced it as the derivative of our coordinate time with respect to proper time. And now using the normalization of full velocity, we've arrived at a fairly nice expression for this gamma, which we can see quite clearly how it behaves from this function here. Essentially, when this velocity is small and nowhere near c, this gamma is just 1. Coordinate time and proper time essentially basically the same thing. But as this gamma now approaches larger and larger values, as this velocity approaches c, we can see that this now proper time is no longer going to be equal to coordinate time. We can quite clearly see why this is now the case. Essentially the solution to this integral is going to become non-trivial, and we're going to have that delta tau is not delta t. And so as this velocity approaches but never actually reaches c, because if it were to reach c then this gamma would become infinite and we can't no longer deal with infinite quantities, but the velocity can limit up to c, and our Lorentz factor is just going to then approach infinity. So we can explore much more the physical effects that this Lorentz factor is going to introduce, and we're going to see that it can be seen to essentially control or parameterize how relativistic your system is becoming, because it's going to affect how much time dilation and how much length contraction the system is experiencing. But all of that to come when we introduce Lorentz transformations.